Welcome everyone. So today we're very happy to have Luca Terenzi from ENS Lyon, and he's going to talk about the six-functor formalism for perverse Norrie motifs. Please.
Okay, well, thank you very much for the introduction, and thanks a lot for having me at your seminar. It's a real pleasure. Oh, and sorry for the wrong date that appeared in the first slide of the presentation. So I will talk about the six-functor formalism for perverse Norrie motifs. This comprises one of the main results of my PhD thesis that I defended a couple of years ago. But I will present my own results at the very end of the talk, and I will spend most of my time just explaining the motivation behind the theory of Norrie motifs, and also why you want to have a six-functor formalism in this setting. So I will use a presentation that I typically use for 60 minutes talks at a very high pace. This time I'm going slowly, and I will try to give some details about constructions that I usually skip. But please, if you have any questions during the talk, don't hesitate to interrupt me. I cannot see the audience now, so if you have any questions, just speak up. Okay, now let me start. So first of all, let me introduce the setting I will be working over. I work over a field K of characteristic 0, endowed with an embedding into the complex numbers that I will call sigma. So what I want to do is to construct theory of motifs over K varieties. And for today, I really need to stick to the characteristic 0 setting. You don't need to take K to be algebraically closed. And also, here I'm assuming that K is small enough so that you can embed it into the complex numbers. If K happens to be so big that this is not possible, then it's not too much of a trouble, because you can always write K as the filtered union of its subfields that are finitely generated over Q, and essentially the theory over K will be the limit of the theory over these finitely generated subfields. If K admits a complex embedding, then typically it could have many complex embeddings, and we will use the complex embedding to perform some key constructions that will allow us to define theory of motifs. But in the end, it turns out that the resulting theory is independent on the choice of this embedding. So just keep the embedding in mind, because we will use it for constructions, but the whole theory is independent of this choice. The objects that I will try to study are quasi-projective K varieties. Here, by a K variety, I mean a K scheme that is finite type, reduced, and separated. And there is this restriction to quasi-projective K varieties. This is a technical restriction. We will see why it comes about during the talk. It also turns out that in the end, you can extend canonically the whole construction to not necessarily quasi-projective K varieties, but let me say that the most interesting part of the construction happens in the quasi-projective setting. Now, after this preamble, let me just explain what is the typical geometric construction we will play with. This is just complex analytification. So to any K variety S, you can attach a complex analytic space using the complex embedding of K. So you just base change your variety over C, and then you consider the set of its complex points endowed with the analytic topology. So if you apply this recipe to the spectrum of K, you get just the one-point space. If you apply this recipe to the spectrum of a finite extension of K, you get as many points as the degree of the extension, and so on. Now, the big theme of the talk will be cohomology theories on K varieties, and more precisely, Q-linear cohomology theories. I assume that most of the audience is familiar with the theory of singular cohomology or any other cohomology theories. Well, you know in this case that you can define cohomology theories with coefficients in many different rings, even with integral coefficients or with finite coefficients. But for today's talk, it's really important to consider Q-linear coefficients, so typically Q coefficients. Okay, now let me state the main result. This is a theorem of which the first part is due to Floriani Morat and Sophie Morel, and the second part arises from my PhD thesis work. So for every K variety S, there will be certain abelian category, Mn of S, called the category of perverse Norrie motives over S. I will define these categories, and the result says that if you take their bounded derived categories, they possess what we call a four-functor formalism. I will explain what this means during the talk, together with what we call a weight structure that is compatible with the four functors in a suitable way, and also what we call Beilinson-Gluring functors. So these are many technical words. We'll explain what they mean in the course of the talk, but as a punchline, we can say these derived categories of perverse Norrie motives have a very rich functoriality and a very rich structure. This is the part of the theorem that was proved by Floriani Morat and Sophie Morel, who also introduced these abelian categories of perverse Norrie motives. And then what I did was to complete this picture by showing that the same categories were also endowed with a closed symmetric monoidal structure in such a way that the inverse image functors arising from the four-functor formalism are monoidal and the so-called projection formulae hold. Again, these are technical words, and I will explain what they mean during the talk. Now, if you combine the two halves of the theorem, you get that the bounded derived categories of perverse Norrie motives enjoy a full six-functor formalism. So four functors come from the first part of the theorem, and the remaining two functors come from the closed monoidal structure. So my goal today is to explain, first of all, what all these words mean, why this theory of perverse Norrie motives is interesting, and then how this six-functor formalism is constructed. So before going to perverse Norrie motives, I want to spend some time on the first instance of this theory, which is what we call the theory of Norrie motives, that was introduced in the 90s by Nadav Norrie. This really justifies the whole theory of perverse Norrie motives. And before even explaining Norrie's theory, I will start with a very general introduction about the general philosophy of mixed motives. This is somehow a niche topic that many algebraic geometers have a vague sense of, but not so many have a technical knowledge of. So I will try to form a precise picture of what we mean by mixed motives, and this will justify the construction of Norrie motives. Then, in order to justify the transition between Norrie motives and perverse Norrie motives, I will spend again some time on the general philosophy behind the theory, and in particular, how the philosophy of mixed motives extends to a philosophy of mixed motivic sheaves. So perverse Norrie motives will come about in the very last part of the talk. Okay, so let's start with a general introduction to mixed motives, and I encourage you again to ask questions if you have any. So, as some of you might know, the idea of motifs is closely related to the concept of cohomology. The idea is that you take a k-variety X and you want to produce linear invariants of it. So typically finite dimensional vector spaces that measure some geometric information about the variety and that allow you to distinguish between non-isomorphic varieties. Now, there are plenty of ways to do that. The first thing you can try to do is to consider Betti cohomology, that is the singular cohomology here with Q coefficients of the underlying complex analytic space. So this gives you a sequence of finite dimensional Q vector spaces, which have very nice properties and a very clean geometric interpretation. They measure how many holes X contains in every dimension, so to speak. And every cohomology theory should be, in some sense, compatible with Betti cohomology. So if you come up with another idea to define cohomology groups of k-varieties, well, you typically want to test that the groups you obtain have the same dimension as singular cohomology groups. Now, the problem with Betti cohomology is that the definition is very much not algebraic. To define singular cohomology groups, you cannot do it with the Zariski topology. You have to use the analytic topology, so the definition is very much not algebraic. But there are more algebraic ways to define cohomology groups. And one example is algebraic de Rham cohomology. So there is an analytic de Rham cohomology, which produces cohomology groups out of smooth differential forms on a smooth manifold. In algebraic de Rham cohomology, you do the same thing, but using algebraic differential forms on an algebraic variety. More precisely, if your variety is smooth, you define the de Rham cohomology groups as the hypercohomology groups of the so-called de Rham complex, which is constructed by taking exterior powers of the sheaf of Kähler differentials. And this gives you a sequence of finite dimensional K vector spaces, where K is the ground field. Now, this formula would not work if you apply it to singular varieties, because Kähler differentials are not well behaved in that case, but there are many ways to extend the definition to singular varieties in such a way that you obtain a well-behaved cohomology theory on all K varieties. So that's an alternative to Betti cohomology. And another alternative, which is very interesting from an arithmetic viewpoint, is given by L-adic cohomology. In this case, L is a fixed prime number. And what you consider is the étale cohomology over the base change of X over K bar with QL coefficients, so to speak. This gives you a sequence of finite dimensional QL vector spaces. So even without going further, we have an infinite family of different cohomology theories over K varieties. These are constructed in different ways from one another, but they are, in some sense, related to one another. In fact, there is a system of comparison isomorphisms relating Betti cohomology to de Rham cohomology, after extending scalars to the complex numbers, and to L-adic cohomology after extending scalars to the L-adic numbers. As a corollary, the different groups that we call Hn of X in different theories, although they are vector spaces over different fields, they all have the same dimension. So in some sense, they provide compatible information about X. But the story doesn't end here, because cohomology of algebraic varieties typically has a very rich structure. And according to the cohomology theory you choose, you typically get a supplementary structure. For example, if you consider Betti and de Rham cohomology, this leads to the notion of mixed Hodge structures. And we know by the Linus work that singular cohomology of algebraic varieties carries a canonical mixed-Hodge structure. So all the natural maps between cohomology groups that you can have must be compatible with this structure, which is a strong restriction to the possible linear maps that can, so to speak, arise from geometry. On the other side, L-adic cohomology groups are naturally L-adic representations of the absolute Galois group of K, and this justifies the arithmetic interest of these groups. And the point is, typically, the supplementary structure you get from one cohomology theory will be not visible on other cohomology theories through the comparison isomorphisms. So each cohomology theory gives you some supplementary structure that you can describe explicitly, but it's not clear what the best possible structure of cohomology groups should be. But this is the starting point of the philosophy of motives, because according to Grothendieck, the different groups that we call Hn of X, different theories, should just be different realizations of a common master invariant that already knows everything about the cohomology of X. And this is what he calls the motive Hn of X. So this should be the deep explanation for the fact that all these different cohomology groups Hn of X have the same dimension, although they live over different fields. Let me now be more precise, because we can state in detail what we expect to get. So this conjecture certainly starts with the insights of Grothendieck, but then it also owes a lot to the work of Beilinson, Deligne, Janssen, and other authors that took Grothendieck's first vision to its current form. So what we expect is that there should be a Q-linear abelian category M of K of mixed motives over K, characterized by a sequence of properties that I will now list starting from the most abstract categorical level and moving progressively to the most concrete and geometric level. So first of all, what we want from this category is that it defines a universal cohomology theory on K varieties, in the sense that it should contain objects that are the universal cohomology groups of K varieties, and the only morphisms in this category between such objects are the morphisms that are that make sense in any cohomology theory, and that arise really from the geometry of K varieties. So this category should keep track of the finest possible structure you can put on cohomology groups on K varieties. It should not just be an abelian category, but a rigid abelian tensor category. So it should have a well-defined tensor product giving rise to a nice duality. Moreover, it should admit weight structure, so there should be a notion of weight filtration for mixed motives, such that the socle of the weight structure is recover what classically we call pure motives. So let me comment on the terminology. If you know about Hodge theory in the linear sense, you might know that cohomology groups of smooth projective varieties underlie pure Hodge structures, and then cohomology groups of arbitrary varieties underlie what we call mixed Hodge structures. In the same way, we call pure motives the motives corresponding to cohomology groups of smooth projective varieties, and mixed motives the motives arising from cohomology of arbitrary varieties. Final property is the deepest one in some sense. It says that categorical invariants, such as morphisms and extension groups, should be computable in terms of the intrinsic geometry of K varieties, in terms of algebraic cycles, and they should be closely related to algebraic K theory groups. Already from this picture, you can understand that constructing the category of motifs should be difficult, because you want to have at the same time natural properties of different nature. You want to have a purely categorical universal property, you want to have some structure, but you also want that morphisms in these abelian categories are related to algebraic cycles. So here is a schematic picture of what I said. The black part of the picture is what we know from classical cohomology theories. We have the category of k-varieties and the different cohomology functors landing in different categories of q-vector spaces. These cohomology functors can be related to one another up to suitable extensions of scalars. Then the dream is to complete the picture by adding the red part. So there should be this abelian category of mixed motifs receiving a universal cohomology functor from k-varieties, and it should realize to the different categories of vector spaces for the different classical cohomology theories in such a way that the whole diagram commutes. So, as you could guess, the category of mixed motifs is not something that has been constructed already. The existence of this category is still widely open, and in fact, it comes down to some deep conjectural properties of algebraic cycles and algebraic K-theory. The good news is, however, that we have at least two ways to produce a serious candidate for the theory of mixed motifs. On the one side, we have the category Mn of k of Norrie motifs over k. This is an abelian category with a nice universal property, but mostly inaccessible to explicit computations. In particular, we don't know how to relate morphisms and extensions of this category with algebraic cycles in a very close manner. On the other side, we have category of Voevodsky motifs that we'll call DMV of k. This is computable via algebraic cycles in the expected way, but it's not an abelian category. It's a triangulated category, and it is not clear from the construction whether you can extract an abelian category inside of it. In both theories, we have both the rigid tensor structure and the weight structure as predicted. So if you remember the four properties of mixed motifs that I listed, we can roughly say that Norrie motifs satisfy the first three of them, while Voevodsky motifs satisfy the last three of them. The expectation is that both constructions recover the correct theory of mixed motifs. In particular, Norrie's category should be the correct abelian category of mixed motifs, and Voevodsky's category should be its bounded derived category. If you're able to prove this, then the whole story is complete. We have the theory of motifs with all the nice feature we expect, because the universal property will come from Norrie motifs, the relation to algebraic cycles will come from Voevodsky motifs. Unfortunately, it's very, very difficult to prove that Norrie motifs and Voevodsky motifs have the expected relation, so that Voevodsky motifs are the derived category of Norrie motifs. Nevertheless, we will see at the end of the next section that there is at least an unconditional bridge between Voevodsky motifs and Norrie motifs, and the two theories turn out to be more deeply related than what appears at first sight. Okay, let me now focus a little bit more on the theory of Norrie motifs. So first of all, I will explain how Norrie's category of motifs is constructed. Let's take a step back. Recall that we have different cohomology theories over k-varieties related by comparison isomorphisms. Now, the idea behind Nori motifs is that you can start from a concrete cohomology theory on K-varieties, and then there is a certain machinery that produces an optimal refinement of the structure of cohomology groups. So the idea is we choose one cohomology theory, which will serve as a model for our category of motifs, and then we construct the category of motifs. So we have many possible choices a priori, but the easiest choice is Betti cohomology. It is not only the easiest because perhaps it's the one we have most intuition on, but also because it has coefficients over Q, which is the smallest possible field of characteristic 0. Nevertheless, since you have the comparison isomorphisms, you would essentially obtain the same theory if you started from the RAM cohomology or from L-adic cohomology. But let's do the construction with singular cohomology. What Nori proved is that there exists a canonical abelian category, which is the category of Nori motifs, defining the finest possible cohomology theory in K-varieties, comparable to Betti cohomology. Probably this sounds a bit vague now, but I will explain what this means in a couple of slides. To be even a bit more precise, so far I've always talked about cohomology groups of single K-varieties, but obviously you also want to consider cohomology groups of pairs of K-varieties, and any reasonable theory of mixed motifs should also contain the universal cohomology groups of pairs. So in particular, Nori's category should also contain cohomology groups of pairs. Indeed,
Luca, sorry,
behind Nori, yes.
Can I ask about the previous slide? So canonical
sure.
means unique up to equivalence, or?
Yes, unique up to unique equivalence, I would say.
Okay. Okay, thanks.
Yes. But actually, I will give a very explicit presentation, so to speak, of this category. I will see it. So the basic idea is to introduce a quiver, which means an oriented graph called pairs over K, in which you put all the features that you want to have on any cohomology theories defined on pairs of K varieties. I'm sorry, there is some background noise. Is it okay for you? Can you hear me clearly?
Yeah, I think we don't hear the background noise. I think it's fine.
Perfect.
Yeah.
Okay, so a quiver is just a collection of vertices plus a collection of oriented arrows connecting the vertices. And here, vertices are labels of the form X, Y, and W, where X, Y is a pair of K-varieties, meaning X is a K-variety, Y is a closed subvariety. And then N and W are two numbers. N stands for cohomological degree, and W stands for Tate-Twist degree. So you should think that this label, X, Y, and W, is a formal replacement of the nth cohomology group of the pair X, Y, twisted by W. Now, there are three types of arrows connecting these vertices. First of all, for every morphism of pairs F, we draw an arrow going from X prime, Y prime, and W to X, Y, and W for any possible values of N and W. So this arrow will keep track of the fact that cohomology is functorial with respect to morphisms of pairs. Of course, typically, when you have a map of pairs, the map in cohomology groups goes the other way around, but we will just invert the orientation of the arrows later at some point. So secondly, if you have a triple of varieties, Y, Z, so Y is closed in X and Z is closed in Y, you also want to add a formal replacement of the co-boundary map that you get in cohomology. So whenever you start from triple of varieties, you get a long exact cohomology sequence where most of the maps in the sequence are functoriality maps, but then there are maps that change the cohomology degree, and these are boundary maps. So we add these boundary maps in the oriented graph. Note that these change the cohomology degree, but keep the Tate-Twist degree fixed. And in fact, there is a third family of arrows which explains what Tate-twisting really is. So the Tate-twist of -1 is tensoring with the second cohomology group of the projective line pointed at 0. So here the fact is that there are many cohomology groups of K-varieties which are one-dimensional, but they really don't look like the 0th cohomology of a point. And the first example is the second cohomology of a curve, for example, the projective line. And if you want to recognize the difference, well, you either go on the category of mixed-sort structures, or you go on the category of Galois representations, and you recognize that this is really not the same as the 0th cohomology of a point, because it's not a trivial object. So we want to keep track of the presence of Tate-twists also in our theory of motives, because you really need Tate-twists to define, for example, Poincare duality in a canonical way. Okay, but now let's forget a little bit of the specifics of the definition. Let's just remember that we have an oriented graph. And now we can define Betti cohomology as a representation of this graph into the category of Q-vector spaces. This means a law that attaches to each vertex in the quiver a Q-vector space, and to each arrow in the quiver a linear map. And this is exactly what we wanted. We wanted that the label X, Y, and W corresponds to the nth cohomology group of the pair X, Y twisted by W. Fine. And now comes the big theorem, which originally was due to Nori in the setting of representations into categories of vector spaces, and then it was generalized by other people to a result about representations into arbitrary abelian categories. The result says that if you start from a quiver D, an abelian category A, and the representation of D into A, there is always a universal way to factor this representation through a universal abelian category A of beta, which receives a universal representation pi from the quiver and maps to A via faithful exact functor. The word universal here means that this category is initial among all the abelian categories giving such a factorization. And morally, what this means is that the category A of beta keeps track of the best possible structure you can put on objects of A, which is compatible with the representation. Intuitively, what you do is you consider the image of the representation into A. This gives you just a few linear maps connecting the objects in the image of the representation, and then you close up this image in a minimal way, in such a way that you still get an abelian category. Now, this might sound like some very easy construction, but it is not easy. It is not easy because you want A of beta to be an abelian category, compatible with the structure of abelian category of A, but you really want iota, this faithful exact functor, to be just faithful, not full. The point is really that morphisms of A of beta should keep track of all the structure that comes from the quiver. So there should be fewer morphisms in A of beta than there are in the abelian category A. Let me maybe sketch how this category is constructed, which will probably shed some light on the universal property. So this is a categorical version of the typical free abelian groups constructions that we do in group theory. So we start from a quiver and we want to produce a universal abelian category out of the given representation. So the first step is to try to make our quiver into an abelian category. And for this, the very first thing to do is to convert the quiver into a category by adding identities and defining a formal composition law, and then into an additive category, and in our case, in a Q-linear additive category. So there is a universal way to do this. This gives you an additive category D+, with the property that for every additive category C, any map of quivers from D to C extends uniquely to an additive functor from D+. So this D+ is not difficult to construct. Then the deep step in the construction is to convert this additive category into an abelian category. And this uses a classical result by Freyd, so-called abelian hull of D+. This gives you an abelian category with the property that every additive functor from D+ into an abelian category C extends uniquely to an exact functor from the abelian hull. Now, these first two steps are just about D. They are not about the representation. But then what you do if you have a representation of D into A is first you extend it to an exact functor from the abelian hull of the additive completion. And then, well, this functor will not be faithful in general. And then the idea is just to take the quotient by its kernel, as you would do if these were just abelian groups. So the category A of beta is defined to be quotient of this abelian hull by the kernel of the induced exact functor beta plus. And you can check by combining all the universal properties in this list that this category satisfies the universal property stated in the theorem. Okay. Now, as you can expect, the category of Norrie motifs is defined exactly as the universal abelian factorization of the singular cohomology representation from Norrie's quiver of pairs. So by construction, what you get is an abelian category receiving a universal representation from the quiver of pairs. So this gives you universal cohomology groups into this category, and having a canonical faithful exact functor to Q vector spaces. This means, for example, that if you take the usual long exact cohomology sequence of a triple, now you can make sense of this sequence as an exact sequence in the category of Norrie motifs, because all the generators and all the arrows come from the quiver, and since the sequence is exact as a sequence of vector spaces, it will be exact also as a sequence of Norrie motifs. So this is a nice category with a nice universal property. The main drawback is that the construction is very categorical. So it is unexplicit, and it gives you no control on the objects, let alone on the morphisms or the extensions inside this category. So except for a few simple cases, it's basically impossible to compute morphisms or extensions in this category using the construction.
Can I ask Luca about
Yes.
the exactness of iota? So it's not automatic, right? So if you have a faithful functor between abelian categories, not automatically exact, right? Or is it?
Right, but this was exact by construction.
Right, but in general, I mean in general. So I mean, if it's an equivalence between abelian, it's exact. But if it's faithful, it's not automatic exact, right?
Right. So here, what I wanted to say is that, so being faithful exact, this functor detects exactness. That is to say, if you have a sequence in the category of Nori motifs and you want to check if it is exact, you just have to check it is exact as a sequence of vector spaces.
Uh-huh.
And
Oh, okay.
this uses the faithfulness because you want to measure that the kernel of a map equals the image of the previous map, which means that the difference between these two guys is 0, and you reduce to checking that its underlying vector space is 0.
Yeah, I see. Thanks. Yeah.
No worries. Thanks for the question. Okay. Now, the next thing is that there is more you can say about this category on the structural side. Namely, you can construct a tensor structure on it. This was defined by Nori, who showed that there is a canonical tensor product on the category of Nori motifs, which makes this category a neutral Tarnakian category over Q with fiber functor given by the forgetful functor into Q vector spaces. So this means in particular that the tensor product of Nori motifs is compatible with the tensor product of the underlying vector spaces. Now, let me comment on this construction because this is not a formal construction. It really uses the properties of cohomology of algebraic varieties. So the idea is that to construct this tensor product, you want to start by defining a pairing directly on the generating quiver in such a way that this pairing is compatible with a tensor product of singular cohomology groups. If you can do this, then by abstract nonsense, this pairing will give you the tensor product that you want. But now, let's see how we should construct this pairing. So if I give you two labels in Nori's quiver, let's assume for simplicity that the Tate twists are both 0 and that the closed subvarieties are both empty. So you just have two varieties, x1, x2, and two cohomology degrees, n1 and 2. And you want to define product of these two vertices. Well, the obvious candidate would be to take the product of the varieties with the cohomology degree n1 plus n2. But now you want that this pairing on Nori's quiver is compatible with tensor product of singular cohomology groups. So what this means is that the tensor product of these two groups on the left-hand side should be the group on the right-hand side. But this is not true in general. What you have in general is a canonical map from the left-hand side to the right-hand side, and the QNet formula tells you that the right-hand side decomposes as a direct sum of terms like the one on the left-hand side, but ranging over all possible pairs of indices that sum up to n1 plus n2. So in general, you will have several contributions, unless, for example, the total cohomology of x1 is concentrated in degree n1, or the total cohomology of x2 is concentrated in degree n2. So how do we solve this issue? Well, first of all, we restrict the picture to the part of Nori's quiver where there are no problems. Namely, we define subquiver pairs 0k, which only takes the vertices x, y, and w such that the total cohomology of the pair x, y is concentrated in the associated degree n. Now, this is just another quiver, so you can still apply the abstract machinery and get its universal abelian factorization that we call Mn0, okay? Now, why is this quiver nicer? Because in this case, you don't get the QNet formula issue that you have in general. So in this case, you can really apply the naive idea to construct a well-defined pairing on the quiver compatible with tensor product of singular cohomology groups. And this gives you tensor product on the universal abelian factorization. Now the problem is to see how much we have lost by passing from the larger abelian category of Norrie motifs to this smaller category, Mn0 of k. And the surprise is that we haven't lost anything, because the canonical inclusion of Mn0 of k into Mn of k is an equivalence. This is really the point that uses algebraic geometry. Let me briefly explain the idea of proof, because it's really beautiful. So the key result is a result by Beilinson that Norrie calls the basic lemma, which asserts the existence of skeletal filtrations for the cohomology of affine varieties. Namely, if you start from a pair of affine varieties, x, y, then you can always find an intermediate filtration by closed subvarieties in such a way that if you consider two consecutive terms in the filtration, xn minus 1, the total cohomology of this pair will be concentrated in degree n. And in particular, it will give you vertex in the smaller subquiver. Now, applying a cellular cohomology argument, you can deduce that if you collect all the non-trivial cohomology contributions coming from the filtration, together with the boundary maps, this complex computes the cohomology groups of the original pair x, y, twisted by W, if you want. Now, what is the point? If you start from a general pair of affine varieties x, y, the label x, y will not define a vertex in the smaller subquiver. So how do you prove that the cohomology groups of this pair actually belong to the smaller abelian category Mn0k? Well, what you do is you take such a filtration, you form the associated complex, and you note that all the objects in the complex are objects of Mn0k, and all the maps in this complex are boundary maps, and these are maps that we included in Norrie's quiver. So this complex makes sense in the abelian category Mn0k, and so its cohomology groups make sense in this abelian category, but its cohomology groups give you the cohomology groups of the original pair. So this allows you to find many more objects inside the smaller abelian category than you would expect a priori. And similarly, you can argue that all morphisms between these objects in the bigger abelian category actually already lie in the smaller abelian category. And so the inclusion is an equivalence. Now, this kind of argument is very fruitful not only for constructing the tensor structure of Norrie motifs, which is what we achieved, but also to construct a bridge going from Voevodsky's theory of motifs to Norrie's theory. Now, due to lack of time, I will not be able to explain how Voevodsky motifs are constructed. Let me say that they are constructed directly as a triangulated category. This category carries a nice tensor product, and also it is endowed with a Betti realization functor into the derived category of Q-vector spaces. So this should be some kind of analog of the forgetful functor from Norrie motifs to Q-vector spaces, just a triangulated version of it, so to speak. Now, what Norrie could prove is that there is a canonical tensor triangulated functor going from Voevodsky motifs to the derived category of Norrie motifs, such that the Betti realization functors can be written as the composite of this realization functor followed by the forgetful functor from Norrie motifs to Q-vector spaces. So this gives you an unconditional comparison functor between Voevodsky motifs and Norrie motifs. And as I said, if you can prove that this functor is an equivalence, then the whole motivic picture is complete. Although now we cannot prove that this functor is an equivalence, having it is already very useful because it allows us to draw an important consequence. So let's play a little bit. You can regard the whole category of Voevodsky motifs as being a quiver. You can regard any category as a quiver by forgetting that identities exist and that composition exists. And you can construct a canonical map of quivers going from Norris quiver of pairs into Voevodsky motifs. How is this map constructed? Well, if you start from a label X, Y, and W in Norris quiver, first of all, you can associate a relative cohomology complex of the pair X, Y inside Voevodsky's category of motifs. Then if you have an entry N in the label, you shift by N in the triangulated category of Voevodsky motifs. And whenever you have a tail twist W appearing in the label, you can also tail twist in Voevodsky motifs. So this gives you a natural way to send objects of the quiver to Voevodsky motifs. And this also allows you to send arrows of the quiver to maps of Voevodsky motifs. And the nice feature is that Norris singular cohomology representation, which is what you use to construct the category of Norris motifs, can be factored through this map of quivers and through the Betti realization. Why am I telling you all of this? Because a formal corollary is that the category of Norris motifs is equivalent to the universal abelian factorization of the representation of Voevodsky motifs into Q-vector spaces, given by taking first the Betti realization and then truncating with the zeroth cohomology group. So the final slogan is that Norris motifs can be directly constructed out of Voevodsky motifs, which is very surprising at first sight. And although this is really an important result in this part of the theory, we will use it in the theory of perverse Norris motifs as a definition. Okay, so this concludes the section about Norris motifs. And now, if there are no further questions, we'll move to mixed motivic sheaves. So this is again a philosophical section, and I will be quite quick on it. So the motivation is that you want to have six-functor formalism in the theory of motifs. Why? Because typically when you study cohomology of an algebraic variety that you are interested in, you often need to relate it to the cohomology of other algebraic varieties, possibly in a complicated way. Some elementary operations that we do all the time is, for example, we divide our variety into an open subvariety and a complementary closed, or we consider open coverings of the variety, or we regard it as a family or a base. So we try to express the cohomology of the total space in terms of the cohomology of the base and the cohomology of the fibers. Or we consider spaces over the variety, such as vector bundles, and possibly many other operations. In all these cases, what's important to keep track of is the functoriality of cohomology. So how cohomology varies when you vary the variety. And as you probably know, sheaf theory was invented as a tool to study the variation of cohomology along maps of topological spaces or varieties in our case. And from a modern perspective, since you want to keep track of all higher cohomology groups and even better of all cohomology complexes, the natural environment to do so is in derived categories of sheaves. So in very abstract terms, we can say that giving a theory of sheaves over K varieties means giving a system of triangulated categories H of S, which are to be thought of as derived categories of sheaves over S. And we want these categories to be related by certain distinguished functors. First of all, given a morphism f from T to S, we want to have an inverse image functor and a direct image functor forming an adjoint pair as in typical theories of sheaves. So here, whenever I write a symbol for one of these functors, what I really mean is the derived functor. Everything will be derived from the beginning. So I will not write symbols of left to right or right derived functors. Now, the direct image, as you know, is a sheafified version of the notion of cohomology. And dually, you want to have a sheafified version of cohomology with compact support, which must be the direct image with compact support. And you want this functor to admit a right adjoint called the exceptional inverse image, so that we have a nice symmetry when interchanging trig functors with star functors. This symmetry should be really arising from duality. And the way to get a duality is with a closed monoidal structure. So over any variety S, you want to have a tensor product functor and internal homomorphisms in such a way that for every object A, you get an adjoint pair as usual. Now, all these functors, of course, have to be related in a certain way. They have to satisfy a list of relations and natural properties. For example, one property you are certainly familiar with is proper base change. And this is something we typically want on every theory of sheaves. Another feature you want to include is monoidality of inverse image functors. So you want that inverse images should be compatible with the tensor product. And note that typically proper base change is really a property that you verify. You have a natural transformation and you check if it is an isomorphism. Monoidality has to be thought of as a structure. You really want to construct these isomorphisms relating tensor product and inverse images. Once you construct the monoidality isomorphisms, you can investigate if the projection formulae hold. Again, this means you have a distinguished natural transformations and you want to check if it is invertible or not. And typically you want this to be the case. There are many other properties that I could list, and maybe this picture will appear a little bit informal, but nowadays there is a very precise mathematical method to encode all the properties you want into a synthetic structure. And this is the kind of structure we call a six-functor formalism. Let me discuss the typical example of a six-functor formalism, which arises, again, from the setting of complex analytic varieties. So the fundamental example is given by the so-called constructible derived categories. For every K variety S you take is the categories of complexes of sheaves for the analytic topology on the complex analytic space S sigma, such that their cohomology objects are constructible sheaves and they vanish out of a certain range. These categories turn out to be stable under direct images, inverse images, and the tensor product, and in fact, they are endowed with a full six-functor formalism. These categories are really the model you have to keep in mind for any six-functor formalism. And even better, inside the constructible derived category, you can find a nice abelian category, which is called the category of perverse sheaves, which has splendid symmetry properties with respect to Verdier duality. I will not explain what perverse sheaves are, but as you might know, they are fundamental objects in geometric representation theory. And morally speaking, they are the correct model for refined categories of coefficients over K varieties. Now, one nice feature of the theory of perverse sheaves is that this is an abelian category that you find inside the constructible derived category. So you can take now the bounded derived category of the abelian category of perverse sheaves, and the miracle is that this is equivalent to the original constructible derived category. This is a famous result of Beilinson, which is absolutely not obvious at first sight. The advantage of using perverse sheaves instead of ordinary sheaves to describe this category is that many interesting geometric structures are better visible in the setting of perverse sheaves. And one important example is the notion of weights. That is a word that already recurred in the previous section. Now, by analogy, there is a conjectural theory of mixed motivic sheaves. The point is, every cohomology theory that we know and love gives rise to an appropriate six-functor formalism. So if mixed motives are supposed to be a universal cohomology theory, they should give rise, in some sense, to a universal six-functor formalism. And this is what mixed motivic sheaves are about. So this picture was conjectured already in the 80s. What it says is that for every K-variety S, there should be Q-linear abelian category of mixed motivic sheaves over S, characterized again by a list of properties that I will state by analogy to the properties of mixed motives, starting from the abstract categorical level, going down to the concrete geometric level. First of all, this category M of S should be a universal version of the classical categories of perverse sheaves over S. Secondly, their bounded derived categories should enjoy a full six-functor formalism compatible with the classical six-functor formalisms on the constructible derived categories. Thirdly, these categories should also carry a suitable notion of weight, namely a weight structure compatible with the usual notion of weights for perverse sheaves of geometric origin. And finally, again, morphisms, extensions, and categorical invariants of M of S should be deeply related to algebraic cycles and more specifically to K-theory groups. So this is an enhancement of the conjectural picture of mixed motives. So it is even more conjectural. But the good news is that, as in the case of usual mixed motives, we have two unconditional approaches to produce some good candidates. On the one side, we have again categories of perverse Norrie motives, which are abelian categories with a nice universal property, but again, mostly inaccessible to computations. On the other side, we have categories of Voevodsky motivic sheaves. These are again related to algebraic cycles in the expected way, but they are not abelian category. They are triangulated, and it is not clear at first sight if an abelian category can be extracted out of them. Now, both settings enjoy both the six-functor formalism and the weight structure. So again, the Norrie setting satisfies the first three properties in my list. The Voevodsky setting satisfies the last three of them. And again, the expectation is that both constructions recover the expected theory of mixed motives, namely Norrie's abelian category should be the correct abelian category of mixed motivic sheaves, while Voevodsky's category should be its bounded derived category. So again, in particular, this means that the category of Voevodsky motivic sheaves should be the bounded derived category of Norrie's. So there should be a close relation between the two constructions, but in this case, the close relation will be really part of the definition of Norrie motives. So this brings me to the last section of my talk, which is about perverse Norrie motifs. This will be the most technical section, and at the end, I will be able to explain how the proof of the six-functor formalism goes.
Can I ask about the previous slide in the mixed motif?
Oh,
so
sure.
I forgot a bit. So mixed motifs was just the same as this, but S equals K. So this is just the relative version of that, or?
Yes, exactly. More precisely, mixed motifs is what you get if S equals the spectrum of K.
But somehow it doesn't look like it looks very different, right? Like, so I don't know, like suddenly you're talking about constructible. I don't know. It doesn't look like just a relative thing. It looks like completely different construction.
No, it's actually that if you have sheaves of Q-vector spaces over spec K analytified, these are just sheaves over a point. So these are just vector spaces. So
okay, thanks.
But I will explain this in the next slide. So let's see. Anyway, as I said, we have the six functors both in the setting of Norrie motifs and in the setting of Voevodsky motifs. And actually, although Voevodsky motifs might look more complicated, it's actually much easier to construct the six operations for Voevodsky motifs, because these categories of Voevodsky motivic sheaves are defined directly as triangulated categories. So the construction of the six operations on Voevodsky motifs started a while ago from insights of Voevodsky himself, which were then systematically converted into a construction by Joseph Ayub in his thesis and in subsequent work. And the construction was then also explored and refined to some extent by work of Szysinski and Église. And there is complementary work in the setting of weight structures by Hebert and Bondarco. So the upshot is that the categories of Voevodsky motivic sheaves possess a full six-functor formalism together with a compatible weight structure, and in such a way that for every K variety S, there is a natural Betti realization into the usual constructible derived category over S. And these operations commute with the six operations on the two sides. So for us, this amazing result will be just a black box, because now we want to study something analogous in the setting of Norrie motifs. And I didn't tell you how perverse Norrie motifs are constructed. I will do it now. Let's take again a step back. Let's go to the last result we saw about the classical theory of Norrie motifs, namely that Norrie's category, which was constructed out of a certain quiver of pairs, can be actually constructed directly out of the category of Voevodsky motifs over K as the universal abelian factorization of the representation defined by taking first the Betti realization and then the H0. Now, this was really the final result I mentioned about Norrie motifs, but now we will convert this result into a definition. In other words, to define perverse Norrie motifs, we will take directly the category of Voevodsky motivic sheaves over S as a quiver. This is what Ivor and Morel did. For every K variety S, they defined category of perverse Norrie motifs over S by taking the universal abelian factorization of, well, the same representation, really, just the analog of the previous one over S. So you first take the Betti realization over S, which takes you to the constructible derived category, and then you take the perverse H0 homology functor, which takes you to the abelian category of perverse sheaves. You can still apply the abstract machinery of universal abelian factorizations to this representation. What it gives you is an abelian category, Mn of S, receiving a universal homological functor from the category of Voevodsky motivic sheaves and mapping to the category of perverse sheaves with a faithful exact functor. So this really takes the shape you want for a category of motivic sheaves. It tells you that motivic sheaves are modeled over perverse sheaves, but the fact that you construct them as a universal abelian factorization means that this category, M of S, will keep track of all the structure that really comes from geometry of varieties over S. Now, this is an extension of Norris theory because by what I said in the previous slide, you recover the category of Norrie motifs Mn of K when S equals spec K. What is the moral behind this construction? Well, we really like the category of Voevodsky motifs, but we cannot extract an abelian category inside of it. And using this universal abelian factorization is, in some sense, a universal way to extract an abelian category inside of it. So if the category of Voevodsky motivic sheaves really had a perversity structure that is compatible to the usual perversity structure under Betti realization, taking the universal abelian factorization would just take the heart of this perversity structure. So in some sense, the definition of perverse Norrie motifs is motivated by the expected properties of Voevodsky motifs. Okay, but unfortunately, we haven't proved this deep conjecture yet, so let us do with what we can and let us play with perverse Norrie motifs as they are defined. Let me go back to the result I stated at the beginning. So the first part of the result is due to Ivor and Morel, and they show that the bounded derived categories of perverse Norrie motifs enjoy what we call a four-functor formalism. What is a four-functor formalism? Well, I explained earlier what a six-functor formalism is in vague terms. Four functors means you just consider inverse and direct images, both in the ordinary version and in the exceptional version. You don't consider the closed monoidal structure for the moment. So the result of Ivor and Morel says that for every S, you have these four functors, and they satisfy all the expected properties. For example, they satisfy proper base change. And most importantly, they turn out to be compatible with the usual four functors on the constructible derived category under the triangulated forgetful functors from perverse Norrie motifs to perverse sheaves. Okay, now this brings us to the question, how would you construct functors on perverse Norrie motifs? These are categories defined out of universal properties. So we do not control explicitly what the objects and the morphisms are in these categories. The trick is to use the universal property as a way to construct functors and natural transformations. So there are some general lifting principles that I will now state in the general abstract language of Weaver representations. So imagine I give you two Quiver representations into abelian categories, beta 1 and beta 2. And now suppose I give you a morphism of quivers, so a map of oriented graphs from D1 to D2, and an exact functor on the underlying abelian categories, such that these commute with the two representations. Then you can show that there is a unique exact functor on the universal abelian factorizations that commutes strictly with the map of quivers and commutes also with the exact functor on the underlying abelian categories up to canonical natural isomorphism. So this gives you a way to lift exact functors to the universal abelian factorizations. And then there is a similar lifting principle for natural transformations between exact functors. So again, let's consider two Quiver representations, beta 1 and beta 2. Then suppose that we are given two maps of quivers and two exact functors as above. So little phi is compatible with big phi and little psi is compatible with big psi. And suppose we are also given two compatible natural transformations, one on the quiver level and one on the abelian level. Then the upshot is that there is a unique compatible natural transformation on the level of universal abelian factorizations that is compatible with everything else. Now, I'm cheating a little bit here because I'm speaking about natural transformations of maps of quivers, which doesn't really make sense. What I mean secretly is that all the quivers I will consider will be actually categories. So we know what natural transformations of functors are, and we will use only those. Okay, now let's play a little bit with these two rules to construct the four functors. So here is the goals of the game. First of all, you want to define one of the four types of functors, say the inverse image functors. And you also want inverse images to be compatible with composition. So this means there should be some natural isomorphisms witnessing this compatibility. So this defines the structure. And then everything else is checking that this structure satisfies certain properties. For example, that inverse images have right adjoints given by the direct images, in some cases also left adjoints, that there are some localization triangles, that proper base change holds, and so forth. So the first step is really to construct the inverse image functors. And for this, we really use the fact that we are working in the quasi-projective setting, because we know that a morphism of quasi-projective varieties can be factored as a closed immersion followed by a smooth morphism. So in some sense, it suffices to construct inverse images just under closed immersions and just under smooth morphisms. This gives you two classes. And then to construct inverse images in general, what you want to do is to paste these two constructions together. Why is this useful? Because you can then exploit the properties of inverse images and the properties of closed immersions and the properties of smooth morphisms separately. What I mean is, let's start from example from a smooth morphism, say P of relative dimension D. Then what we know is that the inverse image functor shifted by D is T exact for the perverse D structures. So it induces a functor on perverse sheaves. And to this functor, you can apply the lifting principle for exact functors, because you have the same functor on the level of Voevodsky-Motyvik sheaves, and the diagram commutes by construction. So you get a unique functor on the level of perverse Nori motifs, which you really want to think of as a shifted inverse image functor. And then to obtain the actual inverse image functor, you go to the derived category and you shift it back. Now for closed immersions, it's not really helpful to consider the inverse image, because the inverse image is not well behaved for the perverse T structure. But the direct image turns out to be T exact without need of shiftings. This means that you can lift the direct image directly to the level of perverse Nori motifs by applying the same game. And so you get an exact functor in abelian categories and then a triangulated functor on the derived categories. But then the construction becomes complicated. And in order to show that inverse images under closed immersions exists, which means the direct image functors you constructed have left adjoints, and also to paste inverse images under closed immersions with those under smooth morphisms, there is another crucial ingredient, which is given by the gluing functors of Beilinson. Now, I will not explain in detail what these functors are, but these are functors that allow you to glue perverse sheaves in some way. The typical situation you consider is you have a K-variety S, you take a global regular function f, and you decompose f into the vanishing part z and the non-vanishing part u. Then, in the setting of perverse sheaves, for example, there are 4 exact functors that are what we call unipotent nearby cycles, unipotent vanishing cycles, maximal extensions, and so forth, that relate the categories of perverse sheaves over S, over Z, and over U in some way. And they are related by certain natural transformations that give rise to functorial short exact sequences. You can lift all of this to the setting of perverse Noether motifs using the lifting principles for exact functors and for natural transformations. And this allows you to lift the so-called gluing formalism for perverse sheaves to the setting of Noether motifs. So the result is that giving a perverse Noether motif over S is the same as giving 2 perverse motifs, 1 over U, 1 over Z, plus some gluing data in the forms of maps from the object over Z and the nearby cycles of the object over U, satisfying a suitable relation. It's not really important to keep track of the details, just the fact that you can glue perverse motifs just as you do with perverse sheaves, which is somehow the same as you do when gluing sheaves. This is very important also for the construction of the tensor structure on Noether motifs. This is what I worked out in my PhD thesis. So the main result says that the categories of perverse Noether motifs admit a closed symmetric monoidal structure, which means you have a tensor product and an internal homomorphism functors such that you get adjunctions as depicted. And again, this satisfies all the properties you want in a 6-functor formalism, including the projection formulae. And moreover, again, this is done compatibly with the analogous operations on the constructible derived categories. Now, again, what do you need to construct the monoidal structure? Well, first of all, you need to construct the tensor product functors and to construct also the monoidality isomorphisms relating tensor product with inverse images. But then you also want tensor product to be associative, commutative, and unital. And in the categorical setting, these are not properties, these are additional structures that you have to construct because they don't just fall from the sky. And you have to make sure these are again compatible with inverse image functors. This is the structure of the monoidal structure, and then there is the properties of the monoidal structure. For example, the projection formula or the existence of internal homomorphisms. So again, there is a part of construction of the structure and then a part of checking the properties. And again, a nice trick is to use the factorization of morphisms of quasi-projective varieties into smooth morphisms and closed immersions in order to analyze the 2 classes separately. And for some constructions, it's also useful to know that it suffices to do them for smooth varieties, and then they propagate automatically over all varieties. But let's leave this aside, because the main task is really to define the tensor product functors. And this is a bit problematic at first sight, because the usual tensor product is not compatible with the perverse T structure unless your variety has dimension 0. The solution is to use the so-called external tensor product, which turns out to be compatible with the perverse T structure in each variable. This is reasonable because in every theory of sheaves, you can define the external tensor product in terms of the internal tensor product or vice versa using inverse image functors. So in some sense, if you construct everything with respect to the internal tensor product, you get everything with respect to the usual tensor product. So let's try to construct the external tensor product. There is another problem here. The problem is that if you try to apply the usual lifting principle for exact functors, you recognize that you cannot do it because the diagram that you want to be commutative is not commutative. So this is the diagram that is not commutative. As you can see, the first half of the diagram is commutative because it's the compatibility of the materialization with the tensor product. But the lower half is not commutative because it's telling you that the H0 of a tensor product is just the tensor product of the H0s, which is not true because you also have other contributions along the anti-diagonal. So this is some sense a more abstract version of the Punnett formula issue that we saw when defining the tensor product on Norrie motifs. In fact, it's really the same issue, just translated in different terms. And now to solve the problem, we proceed in the same way. So first of all, we restrict the picture to a good subquiver of the quiver of Voevodsky motifs where there are no problems. This is the subquiver consisting of all objects in Voevodsky motivic sheaves whose materialization has no perverse cohomology in degrees other than 0. So you take this subquiver, you apply the abstract machinery that gives you a universal abelian category out of it. Let's call this Mn0 of S. And now, by construction, we don't get any problem of commutativity in this restricted setting, so we can define an external tensor product on this smaller abelian category, Mn0 of S. And now again, the problem is to see how much we have lost by passing from the entire category of perverse Norrie motifs to this category, which looks smaller. And as you can expect, the answer is again that we haven't lost anything, because again, the canonical inclusion of Mn0 of S into Mn of S is an equivalence. Let me conclude my talk by sketching the proof of this result, which will be nice because it uses all the ingredients that we collected along the way so far. So the proof goes by Noetherian induction on S. The first case is when S has dimension 0, for example, when S is the spectrum of K. In this case, well, we basically reduced the theory of Norrie motifs over a field, and Norrie's result already tells us that the inclusion is an equivalence. What can you say over a general positive dimensional variety S? Well, what you can say is that the inclusion is at least an equivalence generically, which means if you restrict the picture from S to all possible dense open subvarieties of S, and you go to the limit, in the end, you get an equivalence. Why is that? Well, because in the limit, what you get to is motifs over the function fields of the generic points of S. And again, to motifs over fields, with some care, you can apply Norrie's result. So you get an equivalence. Okay, and then the other crucial observation is that the categories Mn0 of S are stable under a lot of functors, in particular, all the functors that are used to glue perverse sheaves. This is not a deep fact. It's just that Mn0 of S is defined in terms of a subquiver here, which is defined in terms of an exactness condition for perverse sheaves. So whenever you apply a functor that is exact for perverse sheaves, it will respect this condition. And therefore, it will respect its universal abelian factorization. And now it's easy to conclude that if you have generic equivalence and you apply the inductive hypothesis, you get a full equivalence. The idea is, if you have an object in the larger category, Mn of S, and you want to show it belongs to the smaller category, well, what you do is you take a dense open subset such that the restriction of this object comes from the smaller category. Then you consider the complementary closed subset, and you know by inductive hypothesis that also over the complementary closed, the object comes from the smaller category. But then the smaller categories are stable under the gluing functors, so you can glue back these two pieces in the smaller category, and you get an object in the smaller category, which maps to the starting object via the inclusion. So this tells you that the functor is essentially surjective, and arguing in a similar way, you can also prove that it is fully faithful. So this concludes the proof of the proposition, which is really the starting point to construct the whole tensor structure. Then there are many more details and technical problems to solve along the way. But luckily for you and also for me, my time is up. So I will conclude here my talk. Thanks for listening, and let me know if you have other questions.
Yeah, thank you very much for the talk. So is there any questions from the audience? So maybe can you go back to the slides? I wanted to ask something about the third to last slide. So you had this induced external tensor product.
Let me see.
Yeah, so is it the next slide, I think? Yeah.
Okay.
Yeah, so in the induced one in the middle, is it automatic that it is a monoidal structure, or do you have to check something non-trivial? You know what I mean?
Well, the first thing you have is that this functor is compatible with the usual external tensor product. And then you can also check at this level that it is associative and commutative, because sort of you can define what's an associativity constraint for the external tensor product. And you can lift those using the universal, the principles for, the lifting principles for natural transformations, sort of. The complicated part is really to understand unitality, because unitality, well, you really want to have a unit for the internal tensor product, not for the external one. Doesn't make sense. So that's a more complicated part. And so there is something you can construct just by applying these formal lifting principles. Then there is another part that you have to construct on the derived level, let's say.
Okay, I see. Yeah, thanks. Any other question from the audience? Yeah, I saw some people in the Zoom call. I'm not sure if online anyone has questions, but yeah, maybe one more philosophical question. So this conjecture, you have some tensor product on the, you want to have some tensor product on the category of motives, but somehow you're saying that there's no, yeah, it's an extra structure, right? So it's not necessarily unique. So shouldn't we, don't we want to impose some kind of, you know what I mean? Like it should be the right tensor product, not just any tensor product somehow, or doesn't matter?
No. It should be the only meaningful way to define a tensor product. I mean, the uniqueness in some sense is explained by the compatibility with the tensor product of, well, the perverse sheaves or vector spaces in the previous case, and also with the pairing on the quiver level or on Voevodsky motifs in this case.
I see. Okay, so this kind of compatibility makes it the right one. Okay, I see.
Yes, exactly.
I see, thanks. Okay. Any questions? No? Then yeah, let's thank the speaker. Thank you very much.
Thanks for having me.